So now we're going to look at the intersection of a line with a plane. So what are the possible ways that a line and a plane in 3 dimensions can intersect? So our first scenario is that the line intersects the plane at a point. So if we have our plane here, and then we have our line that intersects at a single point. The second scenario, the line is parallel to the plane. So here's our plane, and we have a line that's parallel to the plane. And then our third scenario, we have a line that is on the plane or in the plane. So again, in our first case, we have a single point of intersection or one solution. For our second scenario, we have no points of intersection, so no solutions. And for our third case, we have a line of intersection, or if we like, infinite solutions. There is a way for us to determine which cases we should be looking for. Now imagine I have your equation in Cartesian form. So here's my normal. Notice if the line is parallel to the plane, so the line has a direction vector, let's call it m, that if you were to take the dot product n dot m in this scenario, you should get 0. And that would be the same for this scenario as well. N dot m will equal 0. Again, because if I draw a normal to the plane, it's going to be perpendicular to the plane, but it's also going to be perpendicular to the direction vector of the line. So if you have n dot m equal to 0, you have case 2 or case 3. And for case 1, I get n dot m not equal to 0. So that's how you can verify whether or not a line intersects the plane at a point or is parallel to a plane. So let's look at our first example. First of all, let's check to see what type of intersection we have. So to do that, we're going to take n dot m and see what happens. The normal for our plane is 4, -2, and 1. And we're going to dot that with the direction vector of the line, 2, 3, and 2. And when we do that, we end up with 8 minus 6 plus 2. And that gives us an answer of 4. So this tells us the line must intersect the plane at a single point. So let's find this point of intersection. Let's first write our line in parametric form. So we have x is equal to 1 plus 2t, y is equal to -6 plus 3t, and z is equal to -5 plus 2t. And then all we're going to do is sub the line into this plane. So we're going to sub the line into our plane. And since our plane is in Cartesian form, this makes this a lot easier to determine the parameter t to help us find the point of intersection. So let's sub L into the plane, and we get the following. We get 4 times 1 plus 2t minus 2 times -6 plus 3t plus -5 plus 2t minus 19 equals 0. So next you're going to expand all the brackets and solve for t. So take a moment now and try that yourself, and you should end up with t is equal to 2. Now that I have the t value, I'm going to sub that back into the equation for our line. And if we do that, we get x is equal to 1 plus 2 times 2, which is 5. We get y is equal to -6 plus 3 times 2, which is 0. And z is equal to -5 plus 2 times 2, which is equal to -1. So therefore, our point of intersection, x, y, and z, is equal to 5, 0, and -1. The last thing I'd recommend is you verify that this point is indeed on the plane. We know it's on the line. Since we subbed the t value back into the equation of the line, this is the point it gives us. So now let's make sure that this point is also on the plane. And all you do is take the equation of the plane, which is 4x minus 2y plus z minus 19. And then let's see if we get 0. So we do 4 times 5 minus 2 times 0 plus negative 1 minus 19. 4 times 5 is 20. And then that's minus 20. So we get 0. And now we have shown that this point is also on the plane. So this is indeed the point of intersection between the line and the plane. All right, example number 2. So first, let's check the dot product. So n dotted with m equals, the normal for our plane here is 1, 4, and 2. And we're going to dot it with the direction vector, which we see is 2, negative 1, and 1. Our dot product gives us 2 minus 4 plus 2, which equals 0. And since this is equal to 0, this tells us that the line is either parallel to the plane or the line lies in the plane. So how can we determine which scenario this is? Well, we follow the same steps as we did before. We're going to sub the line into the plane. So we have 2t plus 4 times 1 minus t plus 2 times negative 4 plus t minus 4 equals 0. So let's see what happens when we try to solve for t for this example. So we end up with the following equation, 0t equals 8. So here's my question for you. What value of t can I put into this equation so that 0 times t equals 8? Since 0t equals 8, this means there's no value of t which satisfies this equation. So there are no points at which the line intersects the plane. So this means that the line must be parallel to the plane. And finally, part C. So let's do our check one more time. What does n dot m give us? So our normal is 1, negative 2, negative 3. And I'm going to dot that with 3, 0, and 1. So this gives me 3 plus 0 minus 3, which again gives us 0. So once again, this tells us that either the line is parallel to the plane or the line lies in the plane. So since n dot m equals 0, you can make your conclusion there, same as the one above. Now let's sub the line into the plane. So same as above as well. Sub line into plane, and let's see what happens. So we get negative 4 plus 3t minus 2 times 0 minus 3 times t plus 4 equals 0. And again, you can go and solve for your value of t. And I believe in this one, you end up with 0t equals 0. So in this scenario, no matter what t I sub into this equation, 0 times t is always going to equal 0. So that means any t value will work. So that means every point on the line must be a point on the plane. So this means we have a line of intersection points. So let's state the equation for that line. So therefore, x, y, z, this is the solution to our equation, is equal to any value of t. So negative 4 plus 3t is our x. All our y values are 0, and all our z values are equal to t. And all we need to include is where t is any real number. So any t value we choose will be a point of intersection between this line and this plane. So try the following questions, and good luck.